that peptide bond all across dipeptide, tripeptide, 7 to 8 monomer. This is 7 to 8 residues. And then how that polypeptide assembles to form this jelly roll motif is also part of that backbone motif. So you have to make several combinations of this, right? Where this is a strand, and then you have a loop, and then you have a strand, and then you have a loop. So you have to enumerate different combinations. So this strand maybe is 5 residues, and then the loop is 2 residues. You want another one that is 4 residues in the strand and 3 loops. And then you want the 5 strand with the 2 loops, and so forth and so forth. And you do that for every single strand, every single loop. Then you use, we used what's called fragment assembly. Blueprint Builder, I think, was the protocol that it's called, where you're basically taking short peptide chains or little 3-mers and 9-mers, and you are basically stitching them together to assemble multiple of these different backbones. It's coming from a library of these fragments. I think the Okazaki fragments, something like that is what it was called. And so you're making multiple backbones with that fragment library, and then you're scoring those fragments based on Rosetta energy and a heuristic for delta G of folding. So then you're pruning that, and then finally now you have a set of backbones. Now you want to basically now add sequence to your rotamers, right? You want to make sure your rotamers are actually in the right conformation, that is the lowest energy possible, which would correspond to a sequence that would potentially fold to that. After that, we used to do something called forward folding funding, which was a lot of hand wavy, but we did it, and it corresponded to some semblance of success. And in fact, if you open this paper, you probably will see some of that stuff in here. I don't know if we can open it because I don't know if I have. Oh, I do. Okay, so you see, so this is the backbone enumeration that we were talking about. You can actually see that in this. Oh wow, this is so cool. You can actually see that in here. So I have the protein in pi mole right here in pink, and then you can see the elements that we were just talking about. Can you hear me, Lawrence?
I can hear you.
You can see the elements we're talking about. So this topology has what's called these beta arches. Also, I was saying I was looking for the cover so I can show you the cover off the paper, but anyway, it's on a different day. And if I do a clip, I'll stitch the cover right here. I'll put it right here for you guys. But these motifs, this arch, this beta arch, are characteristic of a lot of beta sheet type proteins. How the beta sheet sandwich basically forms is by having that sandwich together with the hydrophobics in green together. What forms the interlocking sandwich on either side are either hairpins, or because it's non-contiguous paired strands, it's these beta arch loops. And then when there are 2 beta arch loops together, they associate to form a beta arcade. And then this is a solo beta arch on this side.